Okay, the record is now on. So, we have done two major analyses up to now. That is the slope deflection and moment distribution. Slope deflection is the backbone of any structural analysis. Any computer-based program is based on slope deflection, but they use the metrics to solve those equilibrium equations. So slope deflection, no matter how you change the curriculum, it has to be there. Moment distribution, on the other hand, is like it's a subset of slope deflection. It's still very, very useful, because if you know how to say use moment distribution, you can always do a quick analysis on the structure. Now, generally speaking, I have to say that if you mess up the analysis for whatever reasons, unless it is fatal, like if it's a fix and you analyze it as a hinge, that is absolutely fatal. It's unacceptable. Now, let's say if you mess up here, there, everywhere, somewhere, the error would not be so large. So now, when the structure gets complicated, and we all know that it takes time to analyze, so in comes another thing, very useful thing that you need to know. It's what we call approximation analysis. Analysis. Oh, my handwriting goes bad since the morning, so you're gonna have to, if you can't read anything, you have to tell me, okay? This, as the name suggests, we are going to approximate the internal forces of the structure. Okay, so this is very useful if we are going to use for the preliminary design of the structure to approximate the size of the beams and the columns and everything. Okay, and because in the beginning, you should know that from indeterminate structure, the internal forces depend on the stiffness, right? Or EI over F. Now you would know the E, because probably there are not as many materials you could use. You would know the length because you know the dimension of the building, but you would not know the I, which is the property of your section. Correct? So in the beginning, you don't know the stiffness. You can say that because you don't know the I. So we can use the prelim design just to see the idea how big the moment is in the structure, you know, and so we can plan on economy. Because we don't have the size, and you can also use to check on complex analysis as well, because sometimes those who so depend on the program means that they actually don't know the behavior of the structure. You can always use the approximation analysis to give you the broad idea of how your structure will respond to the external load and how much, you know, the forces should be. All right. So that means we're going to approximate it. We are not, it's a good sign, because we are not going to go through those very complex analysis, such as a slope deflection or moment distribution. Okay, so in order to do that, we are going to have to make some assumptions. Assumptions need to be made. And now, you know, things like this occur simply because the engineers back then, they didn't have the powerful tools like we all have now, such as a computer program and so on. So I'm trying to arrange the space here because it's hot, and if I put my body on the nose, it becomes wrinkles by the sweat. So okay, so that's better. All right. So, you know, you can make assumptions and approximate things when you understand what you're doing. That means you understand the behavior of the structure. Okay. So say additional equations are needed. Okay. To eliminate redundance. Do you still remember what redundants are? Okay, when you look at the structure, when you have too many reactions, you can't solve them directly because of the redundance, correct? So we are going to need to come up with some equations to help eliminate those redundants. And that has to be based on sound engineering judgment. Okay. And now, what can we do? We can do that by assume locations of, this is a very important point, it's point of inflection. What is point of inflection? Can anybody recall? What is it? Anyone? Hello? Yeah, I guess that's it. You know, I used to give a lot of weight on the point of inflection in the past, but only like 10% of the students could get there, and it's a very important part of the structure. The point of inflection is the point where your moment curvature changes, right? From negative to positive or vice versa, which means at that particular point, moment must be 0. So if we know some locations have 0 moment, what we can do is we can insert the hinges at that particular location. Okay? We can assume, okay, this is going to be my point of inflection on the structure. And if we know that, you just add the hinge there because you know at that location, moment is 0. Right, so we can safely say that the number of point of inflection should be equivalent to number of redundant. Okay, but oops, sorry. You select the locations of point of inflections and add them equal to the number of redundants that you have, but you have to make sure that locations must be selected so that structure is safe. Okay, for example, let's say for vertical load, say if you have a beam like this, doesn't matter what your load is. Okay, what is going to be your bending moment diagram? Now you see, for students who still cannot differentiate the hinge and the fix, how can you understand something like this? This is a fix, right? So the rotation of the supports are 0, and therefore your beam is going to deflect like this. 0 rotation, but it has to come down. In the end, this somewhere it has to become a positive curvature. So you have the negative at both ends, and then you have positive, meaning your bending moment diagram should look something like this, right? Or maybe I should draw better. Like that. Meaning somewhere here, that's a point of inflection. Right there where moment becomes 0. Okay? So for the fixed end, generally, if a typical fixed support, we can say that this location is approximately 0.2 L if it's a uniform load. So instead of going through whatever method that you have to go through, you just assume that, okay, my hinge is going to be there and put it there. Now, this structure has 6 reactions, right? Now, you -3, because you have the 3 basic equilibrium equations. You have 3 left. Now you assume 2 hinges. And now you know sigma fx, ignore 1 axial force. Then that's it. You can solve the structure. Okay? Let's say for vertical load. The common practice is to assume hinges at 0.1 L. Okay, and then we say the axial deformation is negligible. We can eliminate the another unknown, so we can go ahead and solve that. Okay. Now let's say if we are talking about the vertical load still. Let's say if you face something like this, and if it's only the vertical load, how many reactions do we have here? How many? Nobody's gonna
9.
Yeah, 9. Thank you. So we have 9 reactions. Again, we always have 3 equilibrium equations. -3, you have 6 unknowns left. But because that's fixed, you can assume this hinges at 0.1 L location. So you have 4 more. So we add 4 hinges. And we neglect 2 axial deformation. We can solve it. Okay, or say, then let's say bring it down to just 1 frame. Okay, now it's 6 reaction. Correct. -3. Now you have 3 unknowns left. Add 2 hinges. -2 hinges. And should use that sign. And ignore 1 axial deformation. So we're done. Okay, but that's for the vertical load. Okay, very simple. No need to go through fundamental analysis. But remember, this is the approximation that should give you some idea about how you can calculate. Okay. Now let's move on to another thing, that is the lateral load, because you need to understand and be able to do the frame. So vertical load is like for kids. Okay? So let's have a quick look at lateral load. Okay, this is our focus. Lateral load. To tackle this, we have two approaches or two methods. Okay? The first one is called portal method. You must have heard of the word portal, right? Right? You know what it means? Portal. Nobody knows. This. What? Say that again, please. It means just a door. A portal is a door. But they use this word to call the say something that can warp you to some place else, like a portal. They can call it a door, but it's not cool, right? So let's call it a portal. Portal means a door. Okay, so this was invented by the engineer called Smith, not Agent Smith in the Matrix, but Smith, just the same. This method is, say, appropriate for low building frame. Okay, now when you have the frame and the lateral load, you must know by now that I hope so. I don't think you guys grasp the idea of this just yet. When you push the frame, because many still cannot draw the proper deflected shape. When I push this, generally your frame, because this is fixed, correct? It's gonna go like this. And because this has to come down, you see, this has to go up. So the deflected shape is always like that. But you can't visualize that your beams are going to have the double curvature. Meaning, I can assume that somewhere, because the beam is going to go like that, the column is going to go like that, somewhere there must be the internal hinge. Internal hinge, internal hinge, internal hinge, and internal hinge. You see? So first, we can assume that the A hinges are in the middle of every member. Okay? See how easy that is? So we now, this is the frame with 9 unknowns, minus 3, so we have 6. We add 5 hinges, so we are down with just 1 unknown. Okay? The next one, the next assumption to help eliminate the unknown is that we are going to treat this as a door. You can see, you can view this as, say, one door, see? That's why they call it portal method. That's one door. And then that's another. So this frame, because it has 2 bays, you can call that it has 2 portals. And now we can say that internal frames can be split. You see, the word split doesn't change the form, right? So this is passive voice, but it's still split. And interior columns just equal to 2 exterior columns. Oh, can't spell column. Okay, so you can say that if I have this load P, you split this into 2 doors. We can now say that this is V, 1 shear. And then because this has 2 columns, all right, from 2 doors, 2 portals, the shear here of this internal column is equal to 2 external columns. So this is 2V. We assume that. Then that is another exterior. So we assume V. So from this, we can assume another scenario where P is equal to 4V, and we can calculate another unknown. So we're done. Okay, all unknowns are solved. That's a portal method. Any question? Crystal clear, right? The next one is
In case that,
pardon me.
can I ask?
Yes, sure. Of course you can.
If we have just only two frame, and this one will be a 3 column, right?
Yeah.
We will be changed to individually to V, right? To V will be sum to 4V.
Well, of course, you can always treat, you know, the frame as the portal. So if you have more, you can just treat them like more doors.
Oh, okay.
The internal ones is gonna be 2V because you see, that is 1 column, correct?
Yes.
But then if you look at this as 1 door, and then this is another door. So this is the area where 2 doors are connected.
Yeah.
So you have column from 1 door, you have column from another. That's why the shear is 2.
Oh, okay. I see. Thank you.
Okay, good. The next one is called Cantilever Method. This is by the guy named A.C. Wilson. Nothing to do with the Wilson in the movie Castaway. 1908. Okay. So if the portal method is appropriate for low building, this cantilever method is appropriate for, say, relatively tall building frame. Okay. Again, we're going to use the same approach that the hinges are in the middle. Just the same, but okay. Oh, run out of pages. That's fine. So let's say it's the same behavior. We push the frame to the side, and it's gonna have the same deflected shape like this. Okay. Same deflected shape, fix, and go like that. Go like that. You know, I used to have a toy. I still have that toy at CIA to demonstrate the deflected shape of the frame. Wonder how I kind of didn't use it of late. Okay, so it's like that, and you know you're gonna have the hinge, 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 and hinge, which should be more in the middle. Okay, so again, hinges are in the middle. So it's as before, we have the total of 9 unknowns. We have 3 equilibrium equations, so the unknowns are down to 6. We can add 5 hinges, so the unknown is now down to 1. But this the next thing you need to do, here we need to assume the internal frame can be split. For the portal, we need to assume the internal frames can be split, and we use this assumption to solve for the remaining unknown. But for the cantilever, we're gonna assume differently here. So we will here assume that axial force in columns can be found by distributing forces as if the bending stress no, I need to rearrange. This is a bad grammar. Oops. No, if as bending stress of cantilever. Okay, so here we can look at this building as a cantilever beam. Okay. And like this. So I can easily draw it like this, correct? Because generally, the buildings, when it comes up against the earthquake or the window, it's basically a cantilever beam. So when you know this, when you try to look at the stress, you know this is tension and that is compression. Correct? And somewhere along the line, there is this. What is that? Neutral axis. We can use this to try to approximate the forces in the columns. Okay, so coming from here, now let's say you find the neutral axis of the columns, and now you know the stress is going to occur like that. Let's change the color. And it makes perfect sense because you are, if you're trying to push the frame like this, right here, if you can see equilibrium, here there must be compression to counter that. And here would be tension. And this green couple should give you the moment equal to the moment produced by the lateral load. Correct? So that gives you equilibrium. So with that idea, we can, use the proportion to calculate the force in each column. So let's say if this frame is symmetric, and say that becomes a neutral axis, the force in the middle column now becomes 0. And the force in this and in that will be equal and opposite. If we have something strange, for example, this, maybe trying to be as strange as possible. Based on your equilibrium, this is still symmetric. Okay. that is going to be the profile of your bending stress. Say, make it like that. Okay. The force here will be proportionate, okay, to this triangle. So you can use this relationship to calculate how big each force is. And let's say if you run into something that is not, say, symmetric, like this, say some architect will require, hey, can you do this for me? Say make it extreme like that, okay? Now we don't know where the neutral axis is, but I hope you can calculate the neutral axis, right? So let's say if the neutral axis is here, now the proportion of the force is going to be different. You have to try to locate that and use the correct proportion to approximate force. Now everything will not be equal. Okay, this force will be this much, that much, and that much, and this is like this. But still, the moment produced by these forces in the columns must be equal to the moment produced by the lateral load. And this is the cantilever method, the last assumption that we can use to eliminate the last unknown. So question, please. And it's a lot of fun because you don't have to go through the force method or the this displacement method. We just make assumptions and then go ahead and try to finish the free body diagram and equilibrium, so to speak. That's it. So any questions? And you're gonna have to help me because I may get lost as well. You know, there's plenty of forces. Any question? Hello, are we still awake?
Yes, have.
You are awake. You are awake to the new knowledge, or you just physically awake? Anyway, what? We still have one more question, not question, one more example in the examples volume 2 that you can still use. Okay, we may need number 3 in the next week or so. Okay, whatever that means. So this is going to be the structure, okay, that we are going to approximate. So you see, if you are going to use the force method, I mean, it's impossible. Force method is out the window. If you want to use the displacement method, the slope deflection would mean that how many equations you're going to need? Can anybody tell me? How many unknowns we have? 1, 2, 3, 4, 5, 6, 7, 8, 10 unknowns, 10 equilibrium equations. Wow, that's out of the question. If you want to use a moment distribution, that's going to be some effort, right? So we are going to try to approximate the internal forces in this frame by using the Portal method. Okay. So we need to have high concentration. It's 10 minutes before the break, and I don't want to lose that. So I'm just going to start doing something about it, and then we're going to have a break. Okay. So what does it mean, Portal method? It means that we can assume the hinge in the middle, correct? So without further ado, we're going to assume that we're going to have a hinge here. That's where our point of inflection will be. And here, 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 and on and on. it's not a good idea to talk about this slope deflection because it solves the deformation, right? But when you talk about the force method, now you have 12 reactions, correct? And we have 3 equilibrium equations. That doesn't look like a 3 at all. Let's try again. And we have added how many hinges? 1, 2, 3, 4, 5, 6, 6 plus 8, 14. Really? Okay, the number of reactions that's not enough because this is only the external unknowns. We have 9 more internal unknowns. We have to add to that. We have 6 plus 8, so we have 14 hinges. Okay. 17. Actually, we have, let's say, plus internal unknowns. Okay, is it 14? 1, 2, 3, 4, 5, 6. Yeah, 17. Yes, 14 hinges. And then we are going to assume, we're going to neglect by assuming the shear. Okay. That sounds great. Let me check on that. Okay. We come up with better explanation. So let's keep it that way. But we can solve this very easily. So with that, we're gonna have to assume the fact that the portal means that you now will have here the shear here is going to be V. Here is going to be 2V. Here is going to be 2V, and here is going to be V. Okay, so I'm going to cut the first free body diagram at the hinge. We always cut the free body diagram at the hinge, of course. So now the first free body diagram, I'm going to cut it here. So what I have is something like this. Now, okay. Now I know this is 20. And now I have the total of V here is 6. Okay, so I can say maybe here it's 6V is equal to 20. So V is 20 over 6. So just like that, now we know that this is 20 over 6. This is 2V, so it becomes 20 over 3. This is 20 over 3, and this is of course 20 over 6. Very easy, right? Next. Oops. It's a free body diagram at this location. You know, every year some students will read some textbooks and do something strange about it. It doesn't help solve the remaining unknowns if they use some strange approach from this one. So pay good attention to this. Okay. Now the next free body diagram, meaning we have this, something like this. And here is, this is too close. Here is 20. Here is 40. Okay. So now we have 6V as usual is equal to how much? 60, right? free body diagram. Many of you still don't believe in free body diagram that you write, and you can't draw proper free body diagram, which is really sad. So here a shear is 10, 20, 20, and 10. So it seems like we already solved the base shear, you know, meaning we are now ready to tackle the analysis, or rather the approximation of this structure one by one. Okay, so before we do that, we now solve the base shear. We have applied the hinges. This becomes a perfectly determinate. So any question? Any question? Hello? Okay.
It's not clear ครับ
Crystal clear. No, at this moment, no. So let's stop the record.